Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yes.
Okay. So I wanted to introduce Paolo Biantinesi to you. So first of all, I'm Laurent from the incubation group. And Paolo has been doing his PhD with Robert van de Geen at the University of Texas at Austin on different linear algebra libraries. And Paolo is currently doing his postdoc at Duke.
Yes.
That said.
Thank you. Thank you for having me here. So today I'm going to talk about dense linear algebra libraries. And I will show you two different types of parallelism. So the point being that when we have these multicore architectures, and it's really not clear, even for a pretty standard application like dense linear algebra, it's really not clear yet how to extract the parallelism, how to extract performance out of these architectures. So I will show you a couple of different approaches. And so let me give you what normally it's the outline of a talk in high performance computing when talking about libraries. So the objective is always high performance, and then normally there are some slides presenting some experimental evidence that attaining high performance, it's difficult, it's important, and then there are some slides, some graphs showing that it's important to have many different algorithmic variants, many different algorithms. Probably we also need many different implementations. So what do we need? We need automation. That's pretty much the standard outline. So what I'm going to do instead is do all of the above. Actually, yes, I'm going to follow the same. And then I'm going to show you that when we target multicore, it's not even clear what type of parallelism to target. So it's not even clear how to exploit this parallelism. So the final point is, okay, that we need automation. Now, I want to make a point right from the very beginning that when I talk about automation, I do not refer to optimization as in a compiler's optimization. So I do not refer to, I have a routine or a piece of code and I'm going to try to shuffle, rearrange it, and optimize it. When I talk about automation here, I talk about ways of generating different algorithms. Starting from a mathematical expression, I want to generate different routines, different algorithms. Then each individual algorithm can be further optimized with compilers techniques, but that's not what I am going to talk about today. Please don't be scared about the 57 slides. It's not going to be a super long talk. So I hope in 45 or 50 minutes we're going to be out of here. But please feel free to interrupt. So this is the real outline. I'm going to start with brief introduction. We went past that. I'm going to show actually evidence. So I'm going to go through some interesting performance graphs. Then I'm going to talk about Flame. It's the project that tackles all of the above. I'm going to show you how we deal with automation. Number 5 is what is underneath this automatic system that I will present. Number 6 is a totally different, completely different way of approaching parallelism, and then I'm going to draw some conclusions. Okay, so let's start from some easy example. The Cholesky factorization of a matrix A consists of computing a triangular matrix L such that L transpose equals A. A is a symmetric and positive definite. So we have a problem size along the x-axis and performance along the y-axis. The higher the better. The problem size here indicates that these matrices are dense matrices, and these are pretty gigantic ones for dense matrices. It's up to 15,000, and I'm going to push it even further later on. So what I have here is I used my automated system for creating 3 different algorithms. Again, these 3 different algorithms are have different performance signature, as you can see, have different stability analysis properties, so they are entirely different. In gray, I indicate a LAPAC. So obviously, one of the three variants, the one in blue with the dots, with the circles, clearly what we generated is exactly what a LAPAC has implemented. So what I'm displaying here is performance on a sequential architecture. So this is a single core. And what I'm proving here is that the variant that a LAPAC is the de facto standard for dense linear algebra operations. It's the library. It was implemented in the early 90s, 91, 92, and it was targeting sequential computers as well as sequential architecture as well as shared memory architectures. So the point that I'm trying to make here is that the variant that they selected was almost the best one, was just a tiny bit suboptimal, but really not a big difference. Now, what if we execute the exact same three algorithms, this time on a shared memory architecture? So now the problem size goes much higher, up to 40,000 by 40,000. There are the same three variants, and LAPAC is once again a second best. Again, it's not second by a large margin. So what they did in creating this library, they had to make a decision. So I'm sure they were aware of all of the three variants. They decided that the LAPAC for every operation would include only one variant, only one algorithm. So they chose pretty much a good compromise between the sequential and the parallel case. Over here, parallelism is obtained just by invoking multithreaded BLAS. In case you don't know, BLAS stands for Basic Linear Algebra Subroutines. So linear algebra, dense linear algebra, has this beautiful property that is built on top of very standard layers. The bottommost layers is constituted by this BLAS. So these are very basic routines, matrix multiplication being the most important ones. And every other linear algebra operation is always expressed in terms of these operations. So over here, parallelism is obtained simply by using a multithreaded BLAS. So the algorithms here are exactly the same as in the sequential code, but parallelism is obtained thanks to the BLAS. If you look at the top variant over here, it's the one with the triangles, so variant number 3. If you paid attention, is actually the variant that performs the worst in the sequential case. And by the way, this is also the other way around too. The squares are the best ones in the sequential world. Oh, look at that. They are by far the worst in the parallel world. Okay, let me show you another example, probably even more meaningful. What happens if I run my parallel Cholesky? This time the matrix, instead of being stored in the upper F, in the upper triangular part of the matrix, remember that the input matrix is symmetric, so I will never use the full dense matrix, the full storage. I will only store either the lower half or the upper half. So if I use the lower F and I use LAPAC, here is the performance I get. And moral of the story, if I stick to one single algorithm, you change things just a tiny little bit and you can have performance going, Yes?
Do you have any explanation for why the storage?
It's the access. It's how the memory is accessed. Over here, you incur in huge penalties because the memory, instead of being accessed by columns, it's basically almost accessed by rows. So just this is A is stored in the upper triangular part. Over here, A is stored in the lower triangular part. If you only stick to one variant, things can go really wrong. Okay, let's change operation now. This is the inversion of a triangular matrix. There is a reason why I'm choosing these simple operations. I will get to that later on. Over here, I was able to generate four different algorithms for solving the problem. Again, LAPACK implements one of these four. And again, it's a sort of a good compromise between the sequential and the parallel world. Most importantly here is that problem dimension, okay, this is times 10 to the third. So this is 40,000 by 40,000. Most importantly here is to notice that for small problems, one variant is the best. And then this variant doesn't really perform as good at all. For medium to very large problems, another variant is best, which is not what LAPACK selected. This variant down here, not only it's pretty bad in terms of performance, it's also horrible in terms of stability. This variant is unstable, which means that if we had exact arithmetic, yes, it would compute the exact solution. Since we do not have exact arithmetic, we have round-off errors, this guy actually doesn't converge, doesn't compute the right solution. So the moral of the story is we really need a lot of different variants. We really need a lot of different algorithms. There is clearly no winner no single winner in every possible case. So Flame is the project that tries and tackle this problem, how to create high-performance libraries for dense linear algebra. Flame stands for Formal Linear Algebra Method Environment. It's not a library by itself. It's a set of theories and tools to generate libraries. It's a collaboration of a number of people. Robert van de Geijn is the leader. Ernie Chan is my successor. He's a new PhD student that is responsible for the second part of the talk, for the implementation of the second approach. Kazushige Goto, I think some of you are familiar with his name, is the guru that writes super high performance, low level, super high performance BLAS. He tunes all of these libraries. And then we have a number of collaborators in Europe and at IBM. Oh, well, responsible for the library is Phil Panzi. He's the guy who really put all the pieces together. So an overview of the project. As I pointed out, we always start with a description of a linear algebra operation. So we do not start with a routine. We start really with a mathematical expression. From the expression, we have a mechanical system that is pretty much my PhD dissertation that generates algorithms. This box here is the same as the mechanical system, but this is performed by hand. So as a result, we get to a family of algorithms. And then we have a family of APIs so that these algorithms can be mapped to a range of different architectures and situations. So we have an API for a sequential word. We have a C API, Fortran API, MATLAB Mathematica. We have an API for distributed architectures, API for shared memory architectures and multicores. There is some work in progress on out-of-core APIs. Separate portion of the project deals with the analysis of these algorithms. I'll point out later how the performance and stability analysis of these algorithms is crucial. Actually, I pointed out, I already showed you evidence that the stability analysis of stability properties of these algorithms are important because some of the algorithms that we generate should not even be timed because they do not compute the right number. So a few key features of the project. I think really the most important feature is that we were able to identify the right level of abstraction at which to work and at which to code dense linear algebra algorithms. Thanks to it was because we identified that this level of abstraction that everything else was possible. So we actually shoot for formal correctness. So we do not claim our algorithms to be correct because of testing, but because of a formal proof. And in fact, we use the formal proof to build the algorithms. So we have a proof of correctness first, and we build the algorithm in such a way that is correct. We have a mechanical system to generate both algorithms and code. We generate not one algorithm, but a family of algorithms so that we can attain high performance on a range of situations. Stability analysis, so this is the last chapter of my dissertation. We have a way of, well, we are introducing a new way of establishing properties of these algorithms. And the scope is pretty much dense linear algebra, pretty much the entire BLAS, a good portion of LAPACK, but not entirely. And then the entire RAXI library, which is a number of operations for control theory. Okay, abstraction, as I said, it's the most important thing, so that's where we should start from. This is a representation of the Cholesky factorization. A is input, L is output, L is lower triangular. I indicate L to be the Cholesky factor of a matrix A, like this. Now, everything lays on answering this question. Can I express a matrix L, the solution? Not only, I'm asking myself, can I express the different portions of the solution matrix as a function of different portions of the input matrix? If I can do this, then I'll show you that I can have automation going. So, in order to answer the question, I simply plug this partition matrix into the expression, like this. And now I say, okay, this is what needs to hold. I simplify, and we get down to this expression. This expression is a recursive definition of the Cholesky factorization. Let me spend a few words on what this means. So, first of all, we call it partition matrix expression. It means it expresses the solution, or it expresses different parts of the solutions as a function of different parts of the inputs. It says that the top left quadrant, the top left portion of the solution matrix contains, look at this, the Cholesky factorization of the top left part of the input function, which is great. Okay, then it also says that the bottom left portion of the solution corresponds to this guy over here, and the bottom right quadrant of the solution corresponds to this. If you look at this, just by looking at this definition, it's a recursive definition, one can think of a recursive algorithm for computing the Cholesky factorization. So let's say that we have completed the algorithm up to this portion. Then what we think about doing? Oh, look at this. We could repartition. Now we have 4 quadrants like the recursive definition. So maybe I can compute Cholesky of this quadrant. I can update this guy. I can update this guy. And then I can move on and say, okay, I'm down here, and now I simply have to compute the Cholesky factorization of the remaining part. So it's pretty simple. Then you keep doing that. It's a recursive definition. Okay, so this is how I explain it on the board. When you go and code this up, this is a C implement. Sorry, this is a MATLAB implement. Wait, this is neither. This oh yes, this is C. This is C, and this is MATLAB for a blocked variant. This code, both of these codes, don't look anything at all like what I just presented before. It was very simple. We had everything on the board. We had quadrants and 4 different parts of the matrix, and right here everything is lost. So this is exactly what we want to avoid. And this is how we code it instead. This is how we express the algorithm, and this is how we code it. This is the algorithm. So let me explain step by step. Up here, I partition the matrix in 2 by 2, and this is the corresponding MATLAB function. Over here, I say, okay, I'm done up to this point. Now let me progress. So I repartition this bottom right quadrant. Over here is how I do it in MATLAB. Down here I say, okay, now I'm done. Let's move A11 from the part of the matrix that I still have to operate on to the part of the matrix that I am done with. And then this is the part of the computation, the part of the algorithm where I perform computation. So I will always talk about algorithms and code at this level of abstraction. How do I get high performance? How is it possible to code at this level? Well, we defined APIs. We defined these functions, partition, repartition, continue, so that I can partition matrices in different languages. So once I have that, once I have the partition matrix expression, I told you this is the amount of information that I need for automating the generation of algorithms. Why? Well, first of all, this operation tells me what needs to be done. I need to perform a Cholesky factorization, I need to perform a triangular solve, I need to perform a rank k update followed by another Cholesky factorization. So I know what operations I need to perform. Also, I see that there are dependencies. For instance, L top left here is updated by Cholesky factorization, and then L top left appears on the right-hand side. So clearly there is a dependency. There is another dependency. L bottom left is updated here, and then is used on the right-hand side here. So there is another dependency. So this expression really tells me everything that I need to know to create algorithms. And in fact, from this expression, I can identify loop invariants. Loop invariant, in case you don't know, it's a predicate. It's especially important in computer science. It's a predicate that holds true when you have a loop, and it holds true before the loop is executed. It holds true at each iteration of the loop, right at the top of the iteration, at the bottom of the iteration. And it holds true even when the loop is finished, it's completed. If you can identify a loop invariant, then you can build the algorithm around it that satisfies it. Normally, it's the other way around. The loop invariant is used for proving correctness of algorithms. Normally, you have an algorithm and someone scratches his head really hard and then tries to guess a loop invariant, and then if the loop invariant is true, then goes ahead and proves the correctness of the algorithm. We can do the other way around. We can state the loop invariant ahead of time and build the algorithm around it. So what we say, look at, for instance, at the first expression. We know that we need to compute a Cholesky factorization and then a triangular solve here and then a rank k update here. So I know that I cannot compute everything at once, otherwise the algorithm will not be, otherwise there would not be a sequence of steps. So I need an iterative loop. So I can ask the loop to satisfy these conditions. So I can ask the loop to compute the operation in such a way that the top left quadrant always contains the final solution. Initially, the top left quadrant will be empty, so there is nothing to be satisfied. Then the top left quadrant will be a tiny little block, and what I have to do is to fill it in with the right solution. And then I'm going to try and expand the top left quadrant a little by little until it's as big as the whole matrix. So if I have a loop invariant, I can code it up in Mathematica. Actually, I can code the PME up in Mathematica, the partition matrix expression, and from that I can pass it to my automatic system, and my automatic system returns an algorithm. The algorithm says, okay, I'm going to use this loop invariant, so I'm going to partition the matrix like this, I'm going to progress through the matrix like this, and in order to satisfy this loop invariant, this is the arithmetic operations that you need to perform. And also my system identifies that there are dependencies in red, and so it orders the operations in such a way that the dependencies are satisfied. Now, since there is more than one loop invariant, then my system returns more than one algorithm. Here is a different loop invariant and a different algorithm. Okay, I can do something a little more challenging. This is a Lyapunov equation. This is the equation. Everything is a matrix here. A, X, and C are matrices, and I want to compute X. This is the partition matrix expression for that operation. Once I have that, my system returns an algorithm. Funny thing here is that my system identifies that not only I have to solve another Lyapunov equation over here, but there is also this other symbol. I use this symbol to identify a Sylvester equation. What is a Sylvester equation? It's this guy over here. It's a more general operation. So now, if I really want to compute, if I really want to solve the Lyapunov equation, I also need the partition matrix expression for this operation over here, because I have to compute this as part of the Lyapunov algorithm. So I can type in this partition matrix expression, and my system returns an algorithm for that. In fact, it returns 14 algorithms for this. If I want code, here it is a MATLAB code, and if I want C, this is a C. Again, we have an API. This is a way of partitioning the matrix. This is a way of repartitioning, continue, and these are calls. These are actually not, I had to end code the BLAS calls, to be honest. Okay, the scope, I guess we can skip this slide. So very quickly, I don't want to bother you with details, but very quickly I want to go through a few ideas or a few reasons why all of this works. And then I'm going to show you a different approach to parallelism, a different type of parallelism. So as I said, we not only we shoot for formal correctness, but we actually exploit formal correctness. So we start by identifying an operation in terms of two predicates, the precondition and the postcondition. The precondition tells us what the operands are like, what the contents of the variables are like at the beginning of the computation. So for instance, if I want to invert the matrix, it says, okay, I have a matrix of L of size that it's lower triangular, it contains something, and I call it something L hat. The postcondition tells me what the variables need to contain at the end of the computation so that the computation is actually completed. And it's pretty simple. I want L to contain not L hat, but the inverse of L hat. Okay, once I have the precondition and the postcondition, I can try and build an algorithm so that I can start the algorithm in a condition where the precondition is satisfied, and hopefully it completes in a condition where the postcondition is satisfied. So this is an important point. Having correct algorithms doesn't mean that they are stable. It only means that if I add exact arithmetic, they would compute the right solution. Unfortunately, we do not have exact arithmetic. We always have round-off errors. So on top of formal correctness, when dealing with numerical algorithms, you also want numerical stability, which means that the round-off errors are propagated not too much. A precise definition would involve norms. I don't want to bother you with that. But anyway, we set up this worksheet, and this worksheet resembles a linear algebra algorithm in the sense that it has an initialization step that I call partition, and then it has a loop that goes from 3 down to here. As part of the loop, I have a loop guard, and then I repartition the matrix, so I want to make some progress. I have some computational statements, and then I have a way of making progress. And then what I do, I select one operation that I want to solve, say inversion of a triangular system. I write down the partition matrix expression. From the partition matrix expression, I can identify loop invariants, different loop invariants. I select the loop invariants. Now I'm going to go 100 miles an hour, but that's okay. And I plug the loop invariants in all the places in the algorithms where it needs to be satisfied. Here, 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 here. At that point, I do some magic. And I say, okay, I want the loop invariant to be satisfied here, here, and here. And I also want the algorithm to complete. So I partition and repartition the matrices in such a way that I make progress at each step. At that point, I re-express the loop invariants in terms of these new matrices. And I end up with these two states. One state is what is sitting in my matrix right now, and this other state is what needs to sit in the matrix at the end of the computation. I compare and I establish what computation needs to be performed at each stage. And my automated system does all of this automatically so that you don't have to look at these ugly formulas ever. Okay. Now, let's go to some performance graphs that may be a little bit more interesting. Going to show performance for the computation of the inverse of the symmetric positive definite matrix. Why is this important? Because it's used for computing the gravity field of our planet. So it's also used in tomography. These people in aerospace engineering have these huge problems. Even an improvement of 3, 4, 5% for them was crucial because that would allow them to discard the data more, actually would allow them to either run larger problems or have a quick turnaround on their data. So basically they acquire data from 2 satellites and they have to decide what columns or rows of the matrix to discard and which new columns or rows to add. So the faster they can do that, the more accurate their computation can be. So this operation consists of a Cholesky factorization. Oh, surprise, that's why I talked about it. And then it's normally implemented as a sequence of 3 steps. Cholesky factorization first, triangular inverse second, and then a matrix-matrix multiplication, a special case of matrix-matrix multiplication third. Okay, we generated algorithms for each of the 3 steps, and then we played around with the combinations, and we plotted the results for the best 2 combinations. And you can see that we are somewhat around 10% better than LAPAC. What did we have to do? Really, absolutely nothing. We just asked for Cholesky, triangular inverse, and matrix-matrix multiplication. We generated algorithms and we timed them. So development time was next to 0. And we were able to do better than LAPAC already. Now, can we do better than that? Until now, everything, this was a parallel algorithm, and until now I didn't say a word about parallelism. I simply exploited the parallel BLAS, the multithreaded BLAS. So a natural question is, can we do better than parallel BLAS? So can we create parallelism ourselves? So the answer is obviously yes. So let's take a look at the first iteration of the Cholesky factorization. We have a Cholesky operation up here, then we have a triangular solve here, and then we have a rank k update. Second iteration, Cholesky triangular solve, rank k update. Okay. Well, triangular solve, if I look at the matrix as a block of matrices, Cholesky, okay, once I'm done with this Cholesky, I can actually decompose this triangular solve in 3 blocks, so in 3 different triangular solves. So these can be 3 different tasks to be executed. The moment I execute this first task, I immediately can go ahead and execute this rank k update. I don't have to wait for these 2 tasks to complete. Likewise, the moment I'm done with this task, I free these other 2 tasks, gem, matrix-matrix multiplication, and another another rank k update. So an idea is to actually run the algorithm not on the numbers, but simply on blocks, and to create a list of tasks that will need to be executed later on, like this. But these tasks have dependencies, so it's not just a matter of decomposing the problem. It's also a matter of making sure that these tasks are ordered and executed in the right order. Remember, after the first Cholesky was performed, then the second triangular solves, then the triangular solves can be executed. Only when the triangular solve, one of the triangular solves can be executed, then this circle can be executed, and so on again. So we need a DAG, directed acyclic graph, expressing the dependencies. Once we have that, we can actually execute. We can have 4 different columns, 4 different cores, acquiring tasks and executing tasks independently. So let me explain what I'm showing here. Clearly, there is only one initial tile with a Cholesky. That's what needs to be executed in order to break the dependencies. As soon as the first task is executed by first column, so one of the cores, all the other cores can acquire tasks independently and start working. Now, I am showing tasks in red, black, and blue, representing the 3 different stages. I said that normally the computation of the covariance matrix, that is the inversion of an SPD matrix, is performed as a sequence of 3 steps. Cholesky first, inversion second, and then matrix-matrix multiplication. Well, it turns out that if you break the computation down into pieces, into chunks of work, you don't really need to have this synchronization, such a rigid structure where you have to complete Cholesky, and then you have to complete, in order to have the triangular solve to begin, and then you have to complete the triangular solve in order to have the circ to begin. You can actually just build this DAG with all the dependencies and let the different processors, the different cores, acquire the tasks. And then it turns out that the tasks, and so the 3 operations, are actually interleaved. So you see that there is block before red. Time goes from top to bottom, clearly. So at first, all the tasks executed come from Cholesky. But then we have some black tasks, and the black tasks are associated to the second stage of the operation. So here we have parallelization in 2 different ways. For one thing, each operation is broken down into tiles, and the tiles are spread over the multicores. And second, different stages of big operations are interleaved so that the pipeline is always filled. Okay, this pretty much summarizes what I just said. So we have implemented a component, a new algorithmic component, which we call an analyzer. What the analyzer does is it looks at the partition matrix expression. It's always the same expression that makes automation and makes everything possible. It looks at that expression, and it breaks the computation down into pieces. Not only it breaks the computation down, but it also builds dependencies among these pieces and puts everything into a big queue. And then we implemented, not a dispatcher, we don't have such an entity, but what the multicores perform basically is the implementation of a dispatcher, which is they are sitting, they look at this waiting queue, the global waiting queue, and they acquire tasks when the tasks have no dependencies. As soon as they are done executing a task, they go back into the queue and they free all the tasks that were depending on this task. And then these guys loop until the queue is empty. How do we do this? So this is a C code for the SPD inverse in Flame. So we have a partitioning. Where is it? Here, partitioning. We have a loop, repartitioning. We have Cholesky triangular solve, rank K update, and then we move on. This is the exact same, but on a matrix that doesn't contain numbers but contains other matrices. So it's an hierarchical matrix, and I march through the matrix looking not at numbers but looking at blocks of data. And then I enqueue these tasks, and then I will execute the tasks. Can you see the differences? Probably not, so let me help you. The differences are in red. So most importantly is down here that I need to execute something at the end of the algorithm, because remember the first pass through the algorithm, I really do not execute anything. I simply build and enqueue tasks. Over here I have a FLA, and over here instead I have a flash. Flash means that is an hierarchical matrix. Over here I march through the matrix in blocks of size B, which is the block size. Over here I don't march in terms of blocks. I simply look at the blocks one by one. These are the differences, and of course all of these can be done automatically. Performance-wise, notice the range here goes only up to 10,000. So I am limiting myself to smaller matrices. And what this shows is that these are the variants that I was plotting before that were doing pretty good. In fact, one was doing better than a LAPAC. But over here, I have the variants that implement the supermatrix approach, basically the variants that have explicit tiling. And you see that for smaller problems, they perform better than a multithreaded BLAS. Why? It's pretty simple, actually. The multithreaded BLAS has everything in dense linear algebra, almost everything in dense linear algebra, is tuned for very large problem sizes. The new approach, the supermatrix approach, do not have a very large operands. The supermatrix approach creates small tasks. The idea is to fill the multicore as soon as possible. Even when we have a small problem or a large problem, we want to create small chunks of data that the multicore can operate on. And so that's why the supermatrix approach behaves even better, performs even better than the multithreaded BLAS for smaller problem sizes. Then it plateaus, because clearly once the pipelines are full, it doesn't really matter how many more tasks there are in the pipelines. They will always operate at that rate, and that's the rate that it's shown here. On the other side, when you have a multithreaded BLAS, you really rely on the performance of the multithreaded BLAS, and you know that the larger the matrix, the better the performance. So eventually there is going to be a crossover, and I'll show you the crossover later.
Variants and variant 1 and variant 2 and variant 3, and over here you're showing that by pipelining it well, actually all 3 variants basically give you the same performance?
It's not just by pipelining well. It's a good question. The answer is that when I break the computation down, you have to perform exactly the same arithmetic computation. If you look, now it's true that the algorithms are different, but now I'm breaking down the algorithms and I'm looking at the unit of computation block by block. And that's pretty much identical. It might be in different orders, so there might be very tiny differences. But now if you look at the list, at the sequence of blocks, at the sequence of tasks, they are exactly the same for the 3.
Shouldn't you expect similar performance curves basically when you do variant 1 and variant 2?
No. These are not the same. Only when you break them down, they are the same. When you look at the operation itself, it's not the same at all. Say, on one side you can have a triangular solve on matrices of a certain shape. When you decompose it down, you have triangular solves of squares. On another algorithm, you may have a gem on matrices of a completely different shape, and the shape plays a huge role in dense linear algebra. But when you
for that in your supermatrix variants,
it's not what?
Why is that shape basically not playing a role in there?
Because
they're all the same?
Because the shape here plays a role. Over here, what I've done is I eliminate the shape. I break everything down to be a unit, a block, a single block. So basically, yes, there are tiny little differences. These blocks...
Actually, with and without that pipelining, basically like what would you basically get if you just take the shape, remove that shape variance out? How much performance difference would that actually give you as opposed to basically adding the pipelining?
How can you remove the shape?
Just as you've done for the supermatrix variants.
I think he's saying if you partition the matrix in subblocks, that you will execute sequentially, right?
Just a sequential variant by removing that particular factor. If you say that factor basically makes a big difference in the
which
performance.
factor, I'm sorry?
The block size factor that you're talking about.
The block size plays a crucial role. Because,
big difference between the 3 variants, and if it doesn't make a difference in your...
No. The blocking factor doesn't differentiate. It's not different in the 3 variants. I say that the shape of the matrices and the different algorithms. If you look at the algorithms, let me show you. Two different algorithms. That's the algorithm 1 and algorithm 2. Okay, over here we have, this is a rank K up, this is a triangular solve and this is a Cholesky. If I show a different algorithm, I have a completely different operations. So if you, yeah, that's what makes the difference, not the blocking. If you look at the operands of these operations, you'll see that the shape of these operands is different. It's not the blocking. The blocking is always the same. In fact, well, okay. Okay, let's talk about this later. So I got to the point that performance of the supermatrix approach was better than the multithreaded approach for small problem sizes. Here I want to show you that there is no trick. If I store the matrix, if I ask for the lower triangular version of Cholesky, remember that's where you get a flat performance down here. With supermatrix, you get nothing like that. And this is plotting larger problem sizes, and you see that supermatrix plateaus while the multithreaded variants keep increasing in performance. This slide also shows that depending on the BLAS that you use, well, for one thing, the crossover changes, but also it's interesting that, say, if you use the Goto BLAS, then you see that the supermatrix, sorry, so let's compare Goto BLAS with MKL. MKL is a BLAS from Intel. So if you compare the two, on supermatrix, you see that the MKL BLAS attains a better performance. On the multithreaded instead, you see that Goto BLAS attains quite a bit better performance. Why that is the case? Because MKL, it's better tuned for smaller problem sizes, and that's exactly what supermatrix uses, while Goto does an amazing job for large matrices, and that's why the multithreaded BLAS, the multithreaded variant is on top. This is just to convince you that having having a variety of algorithms is a good thing. Over here, I am running the same algorithms, but on a distributed memory architecture, and I'm showing that just by combining the good algorithms together, we were able to gain 20 to even 30, actually 20, 25 to up even 30% performance with respect to scale APAC. Here I have processors and I have performance per processor, and so this was a really big gain for the guys, the aerospace engineering guys. Okay, conclusions. I think I am in time. Yes. We wanted to create high-performance algorithms and routines for dense linear algebra. I showed you that automation was possible thanks to the partition matrix expression. We were able to automate the generation of algorithms. We were also able to automate the breaking down, the creation of tiles. So we not only attain formal correctness, we really use formal correctness to generate algorithms. We generate family of algorithms. And I showed you that we generate two types of parallelism, or at least we shoot for two different types of parallelisms. For both types have merit. For small problem sizes, the tiled approach is superior. For large, very large problem sizes, the multithreaded approach is superior. In the future, what we need to do is we would like to have performance tools so that we do not have to run all these algorithms to identify which one is best in what scenario, but we would like to be able to predict performance. So, thank you. Yes?
Yes, I work with number theory, and my matrices are likely to be modulo primes or over finite fields. Is anybody working on generalizing this type of software to work there?
Let's see. I think that when I visited the University of Washington, someone gave me a paper exactly on that. We have never looked at that problem specifically. No, I think someone right here in Seattle, they have. Huh. So I'm sorry, no. Yes.
So for the automation, so basically you want to first partition the problem, then you find the loop invariant, right? For partition, is there only one way to partition? Suppose you have multiple ways to partition.
You have multiple ways. That's right.
As usual, recursive only the left to right hand stuff.
Well, yes, I skip that detail. Normally, in fact, you need more than one way of decomposing the problem, because what I showed you in all the examples, I always showed you that we traverse the matrix in one single way, from the top left down to the bottom right. That's actually not true in generally speaking. You also need ways of decomposing the problem, say from left to right and from top to bottom. So you're absolutely right. You need more than one way of decomposing the problem.
For those that parallel the tiles, how could you decide to say choose the tile? How could you partition the problem? Say, okay, I choose the tile.
Okay, yes, that's also a good question. So over here, I decide to break the problem down into tiles. What I do, I call Kazushige Goto up and I say, hey, Kazushige, tell me what do you optimize your matrix multiplication for? He tells me 216 or 128, and I partition accordingly so that I exploit the maximum performance out of the BLAS. Yeah.
So your supermatrix numbers are pretty good, but I have not seen a single graph where those numbers are different for the different variants. I mean, do you have cases where they are different?
It doesn't really happen that much. No. They really over.
Language. I mean, it seems like one variant that you basically, if you can do one variant and basically pipeline it well, I mean.
Yeah, absolutely. This is just for academia. This is just to prove a point. Yes. That's for sure. Yes, I agree.
So you gave results for Cholesky and supermatrix. You had implemented other factorizations, I assume.
Yeah.
And what properties? Because Cholesky doesn't have pivoting. For
Yeah. Pivoting is a big thing.
So again, to other factorization algorithms, do you see the similar kinds of results?
Pivoting would break the decomposition down entirely. So for pivoting, we have a workaround, which is a different. Say for LU, we have a different type of pivoting. If you really want to bring the real pivoting in, that's totally different story. Yeah, we haven't looked into that yet.
Those workarounds and what the other factorization algorithms that you've implemented, do you see similar performance curves?
Yes, always, yes. For small problem sizes, yes, because basically what we get, we feed the multi-beasts, the multi-core beasts, faster. We are able to create small chunks of data, chunks of work that they can tackle earlier on, and they stay the beasts, the multi-cores. They stay eating the whole time.
So you've compared with multi-threaded LAPAC. Have you compared with the multi-threaded factorization routines in MKF? So not using just the BLAS in MKF, but the actual Cholesky factorization.
I don't know why we have not done that. I assume they're not as good. I don't know. I cannot answer that. I'm not sure. Yes.
So you say that you break up into these blocks so that you can get computation started faster.
Yeah.
Have you looked at, say, an approach where you would start out with small block sizes so you can get a quick startup and get bigger blocks?
That's a very clever idea. We had that idea. We haven't implemented yet. Yes, Yes, absolutely. It's a little trickier than that because I don't know if I should get to this level of details, but when the multicores acquire a task, they do not acquire the task randomly. We also assign a weight to each task, and the weight depends on an estimation of the cost. And you want larger costs, larger weights to be executed earlier on. So what you're doing goes a little bit against what you're suggesting, goes against that because you would create light blocks earlier on. You would create lightweight tasks. But yes, we have thought of that. We have not implemented that yet. Yes.
Okay, I'm sure. So because I read the proposal of the Robert, so is there this approach basically will fit to all of the LAPAC, the routine? Seems like there's something, as I remember, there's some fundamental problem not able to solve.
Yeah, sorry. No, I skipped that slide. That's true. No, we cannot cover the entire LAPAC. Here we go. Anything that has to do with SVD and with eigenvalues, vectors, we cannot do that. There is a simple reason for that. These operations do not have a PME, a partition matrix expression. In other words, say if you have I don't know if you're familiar with eigenvalues, but it's not possible to say, oh, this eigenvalue or this set of eigenvalues, it's not possible to express them in terms of a subset of the input matrix. Each eigenvalue depends on each entry of the input matrix. You cannot have a recursive definition. So whenever you do not have that recursive definition, which I call partition matrix expression, you cannot apply this methodology. Thank you. Thank you.